This is Dr. Sridhar. Came back to you with another video lecture on phase and phase angle calculations and phase difference in alternating quantities. This will highly helpful for us to know the impedance of AC circuits, because in DC circuits the line will offer only resistance to the incoming electrical quantities. But whereas if you are talking about AC circuits, in the AC fundamentals, now in addition to the resistance of the line, so another opposition it will be caused because alternating quantity will have some frequency in it. So because of this frequency, alternating quantities will get some other opposition by another electrical parameters. That another electrical parameter is nothing but reactance of the line. The reactance will be offered by inductance and the capacitance. So before proceeding to reactance and other associated parameters in alternating quantities, first let us talk about what is phase difference. So with this simple animation, we can come to one simple conclusion in what way that phase of alternating quantities can be defined more preciously. So the phase difference between two electrical quantities is defined as the angular phase difference between the maximum possible value of the two alternating quantities having the same frequency. So as we know that DC quantity will not have any frequency in it, and whereas AC quantity will have some frequency. As per our Indian standards, the AC quantity will have some 50 Hz frequency, 50 plus or minus some small acceptable value in the frequency. So in the majority of the cases, frequency can be taken as 50 Hz. So this 50 Hz cycle we can draw, like suppose now if you're taking a cycle like this, so this is the one alternating quantities. Now we have defined what is the time period of this particular signal. So this is nothing but this is the time period, and this is nothing but alternating quantity. This is might be voltage or it may be current. So this is nothing but it is a time. So this voltage is nothing but it is varying alternatingly. Now having a time period, now this particular voltage or current wave is having a time period of capital T. So this T can be defined as, this is nothing but it is a time period of the waveform. So this is nothing but reciprocal to the frequency. Now suppose if we have a frequency of 50 Hz, then it will have some time period in it. So any quantity, suppose if you are taking it is a DC quantity, now if it is having continuous magnitude, now even if you are varying from T is equal to 0 to infinity, if this quantity is having constant voltage or current, so this amplitude is nothing but it is independent of the time. So always it has some constant magnitude. The constant magnitude may be X units or Y units based on the voltage value or the current value which was represented on the y-axis, or which was represented on the represented for voltage or current. Suppose now if it is 10 units, so this 10 units is nothing but it is not periodic. So it is continuously, it is constantly having its value of 10 units from T is equal to 0 to T is equal to infinity. So this magnitude is nothing but it is throughout the time period. So from T is equal to 0 to infinity, this is having a constant value, that is 10 Hz, for which we cannot define the frequency. So frequency we cannot define. So if the frequency is not definable, T is also not possible to define, because now there is no alternating quantities in the waveform. Now it is having constant magnitude. So this is called as a DC system. This is DC waveform. So direct current waveform. So it is having constant magnitude from minimum value of the time to the maximum value of the time. For such cases, defining the time period or defining the time or defining the frequency is immaterial. Is not the way of defining the frequency or time for DC quantities. But coming to the AC quantities, alternating current quantities, in this one, now from T is equal to 0 to T1, now it is having positive alteration. So positively it is varying like this. From T1 to T2, now the waveform is nothing but it is moving like this. So it is moving in the negative direction. So it is having some negative alteration. So the set of one positive and one negative alteration, provided that 0 to T1, what is the base? That base must and should be same from T1 to T2. In such cases, now this is nothing but this is called as one set of one alternating quantity. So one set of alternating quantity can be spread on the system for a time period of capital T. The time period capital T can be defined as, or it is inversely proportional to the frequency. So frequency is definable. So automatically time period is also definable. So this alternating quantity is nothing but all the alternating quantities will have some frequencies. So whenever the frequency exists, so what happens now? So from t is equal 0 onwards, if you are analyzing the waveform, from t is equal 0, now sinusoidally the voltage, now let us assume that is a voltage quantity. Now from t is equal 0 onwards, if time increases, so voltage is also sinusoidally increasing after reaching to a maximum value. Again, even though again if you are increasing the time period furtherly, then again your quantities goes on decreasing. At t is equal to t1, that quantity is reaching to 0. Then again furtherly if time increases from t is equal to t1 onwards, now it is negatively increasing after reaching to a negative peak. Again furtherly if you are increasing the time period on the x-axis, so again it will go back to the 0 quantity. So like this alternating quantity is varying its value. Now if you are changing the time value from t is equal to 0 to T1, T2, so and so. And furtherly beyond t is equal to T2 also, if you are varying the time period, now it is going to complete one more alteration cycle. Thus the same thing we can see in this animated video. Now suppose if you are varying from t is equal to 0 to up to pi by 2, now at this pi by 2, it is reaching to the maximum positive value. Then again from pi by 2 onwards, now at t is equal to pi, what happens? Again it go back to the 0 value. From pi onwards also, if you are increasing at 3 pi by 2 at this point, now it is reaching to the negative maximum. So negative maximum. And furtherly if you are increasing from 3 pi by 2 to 2 pi, then again it is going back to the 0. So what is my intention with this animated video is, so what is the peak of alternating quantity? What do you mean by 0 crossing points in the alternating quantity? So this is a 0 crossing point. Means at t is equal to pi. So or at omega t is equal to pi, what happens? The waveform, or this is a, let it be a voltage V. The voltage is nothing but changing its phase from positive direction to the negative direction. So till t is equal to pi minus. So just before this instant, so it is having the positive value. Now t is equal to pi plus onwards. So slowly, just immediately after crossing this pi, omega t is equal to pi, now it is changing into the negative direction. So what is the cutting point between the positive and negative? Means that is at omega t is equal to pi. This is the point where the quantity is changing its value from positive to negative. So this is at omega t is equal to pi. This is nothing but the 0 crossing point. Similarly, another point. Now if you are taking omega t is equal to 2 pi, at this point also, now just before reaching to the omega t is equal to 2 pi, now the waveform is having, or this quantity is having the negative value. Means now just up to omega t is equal to 2 pi, now the variation is like this. So it is having negative. From omega t is equal to 2 pi onwards, it is going to complete one more alteration cycle. So this is called as a positive side. So this omega t is equal to pi, omega t is equal to 2 pi, these are nothing but the 0 crossing points, and this is the positive peak, and this is nothing but the negative peak. So in one complete alteration having a frequency of 50 Hz or having a time period of t, now you can find one positive peak and you can find one negative peak. Now this is about one single waveform, but now the phase or phase difference, now it can be defined more preciously if you are taking two waveforms simultaneously. Suppose here I am taking two waveforms. In this particular case, one is shown with the green and another one is shown with the red color. So this green is having positive peak at this point. So this is nothing but the peak value of the green waveform. So next one is, now if you are taking the red waveform, now the waveform shown in the red color, so this is nothing but it is peak. So these two are the positive peaks. Similarly, if you are taking, so this is the negative peak and this is the one more negative peak. Now, what is the difference between two positive peaks? The positive peaks means two waveforms. If you are imposing a single graph, now if you want to determine the phase difference between two waveforms, means now you please pose two waveforms and single graph, and you compare whatever the adjacent difference between two positive peaks or two negative peaks. The difference is nothing but that is called as a phase angle difference, or this is represented as a phase difference. So not only the positive peaks you can compare, sometimes you may also compare what are the zero crossing points. Now what is the difference between them? This difference is also called as a phase difference, that is pi. So either you can compare, if you want to calculate the phase difference, you can compare two positive peaks or two zero crossing points. So whatever the space difference between them means, now if you are talking about the peak values, means the two waveforms positive peaks only you have to consider, and the angular difference between two positive peaks is nothing but that is a phase difference. Similarly, you can also use the same concept to know the phase difference even by having the knowledge of negative peaks as well. So this is the negative peak and of the waveform shown in the red color, and this is the negative peak of the waveform shown in the green color. So what is the space difference between them? So this is also called as a phase difference. So this is how we are going to define the phase difference with the help of positive peaks, means this is this, or else you can compare zero crossing points also. So this is the zero crossing point of a waveform shown in the green color. This is a zero crossing point of another waveform which was shown in the red color. So with the help of these zero crossing points, how we are going to determine the phase difference means this simply what is the angle difference between them. So that is nothing but it is a phase difference. So how can we define what exactly the definition of this phase difference means? The two alternating quantities have phase difference when they have same frequency but they attain these zero values at the different instant. So this is the one instant and this is the another instant. What is the difference between them? So that is nothing but it is a phase difference. The angle between two 0 points of two alternating quantities is called as angle of difference. So in the two waveforms, now here in this example we have taken two voltage signals or current signals, or simply we can say that two alternating quantities, and these two alternating quantities must and should have the same frequency in it. Now if the frequency is different, so the phase difference calculation is irrelevant. So first of all you have to ensure whether the frequency of the two alternating quantities is same or not. Once if it is same, then you can compare the two signals to know the phase difference. So again one more alternating animated video with which we are going to elaborate how this phase angle and phase difference can be contributed here. So this red one is nothing but, this red quantity is nothing but it is an imaginary quantity. It is only moving in either 90 degrees. So this point is 90 degrees point and this is nothing but a 0 to 70 degrees point. So 0 degrees and this is 90. This is plus or minus 180 degrees. This is 270. This is 0. So this red color, which is only just, it is moving up and down. So it is 90 degrees. Now once it reaches to the 180 degrees, again it come back to the 270 degrees. So this is perpendicular quantity, and this blue one is nothing but it varies from either 0 or 180 degrees. So horizontally it is moving here, and this red one is nothing but vertically it is moving. So if you want to find out the resultant between them, the resultant is nothing but it is shown with the green color component. So this is about a simple animation one. Now the same concept if we want to use in the sinusoidal cases, now two alternating quantities. The two alternating quantities means one is with of the green, one is with the blue and one is with the red color. So the red color waveform is like this and the blue color waveform is like this. Then whatever the resultant of these two, which is shown with the green color. So the resultant is nothing but as time progresses or the phase angle progresses, automatically the resultant is remained same, but the phase angle or the angular difference between the two quantities changing. At any instant if you could see, now at this point the green is 0, but whereas the red is nothing but it is 270 degrees. So that's how the phase angle can also be computed here. The phase angle is 360 degrees and it is again varying from 0, 95 or 90, 100, 180, 200 and up to 360 degrees. So this is one more example. Now radians and degrees also we can compute here, and this is at the 0 degrees. Once if the component changing, it goes on increasing, automatically it can make one complete envelope of the alternating quantities. Now this will help us how this a single unit circle radius or central circle can make some complete one cycle means. Now the same quantity, now you can represent, now here this waveform is spread from 0 to 360 degrees. But here the same 0 to 360 degrees we can represent in one concentric circle. So this is 0 degrees, this is 90 degrees. Whenever it is varying from 0 to 90 degrees, now you can get one complete quarter cycle here. Again from 90 to 180 degrees, again you can complete one more quarter cycle. So how we are going to see one half cycle. Again furtherly if you are increasing 180 to 270 degrees, you can get the one more negative quarter cycle. From 270 onwards, you can see one more quarter cycle. Like this, we are going to get one complete alternating quantity envelope. So one more important point here is leading quantities and lagging quantities. What do you mean by leading and lagging and reference one? So suppose in the first waveform, if you could see, now this waveform is nothing but it is goes on increasing and again it is coming back to 0, and this is at t is equal 0 instant and this is at t is equal some finite value. Let us say this is some time t and this is the time axis. So how can we represent these alternating quantities? This alternating quantity, let this waveform is A. So this A is nothing but it depends on the time t. So A of t, so A of t is nothing but whatever the peak value is nothing but the A max. So A max into sine of omega t. So this is the representation of this. So here in this simple example, the waveform it is originating at t is equal 0. That point is nothing but it is a reference point. Generally this t is equal 0 is a reference point from where our alternating quantities begins. Now coming back to the second waveform. Now actually this is our reference point, but that is not originating here. Now it was originated before t is equal 0 instant somewhere here. So this point is nothing but not the reference point. T is equal 0 is nothing but it is a reference point, because now we can say that this is the reference waveform. This reference waveform, now it is originating at t is equal 0 and it is completing one positive half cycle at t is equal pi, and from pi to 2 pi it is completing one negative half cycle. So this is nothing but a complete envelope of one alternating quantity. So we can take this as a reference waveform. So with respect to this reference waveform, now suppose if you are comparing this particular waveform and the second waveform, it is instead of beginning at t is equal 0, this was advanced by some pi angle. So some phase difference is there between t is equal 0 and the originating point of this waveform. So this is nothing but this is called as the angle of advance. So angle of advance, so that is nothing but the positive, angle is nothing but the phase. So this particular waveform is having some angle of advance, or that is nothing but the positive phase. So positive, so that was represented as a plus, and the phase is nothing but the pi. So how can we represent this? This is also, of course, it was originated instead of t is equal 0, somewhere at t is equal other angle, which was advanced by an angle of pi. So even though this is nothing but the alternating quantity, now exactly in the sinusoidal form. So and this quantity is nothing but the alternating. So A of t is equal A maximum into sine of omega t. Some angle of advance is there. So this is the positive and this is pi. So the waveform, now if it is, now if this is the waveform, then whatever the mathematical equation of this particular waveform means, this A of t is equal A maximum into sine of omega t plus pi. So this is about the second one. Now coming to the third one. Now this is the t is equal 0 is nothing but this is the reference point. This is our reference point. Now instead of here, this is originating at some other point. This is the point. So this is not advancing, neither starting at the reference point, it is lagging. So it is behind this t is equal 0 point. So this is nothing but angle of lagging. So this is called as a negative. Lagging is nothing but the negative, and angle is nothing but the it is phase. So negative and minus pi. So this is minus of pi. So the waveform is nothing but how can we represent? So whatever the mathematical equation of this particular waveform means, A of t is equal A maximum into sine of omega t minus pi. So these are the three ways. Either now if you are taking any waveform, either it may start here or may advance by some angle or it may lags by some angle. So only these three possibilities are there if you are taking this as a reference. So if this is our reference, now reference means t is equal to 0. Now lagging means minus pi. Leading or angle of advance means this is nothing but the plus pi. So only these three cases may occur. So that's why we have depicted this particular case by taking three different sinusoidal waveforms originating at different instants. Now in the first one, at the reference point at t is equal to 0, it is originating. And the second case, not at t is equal to 0, it is advanced by angle pi. And in the third one, it is lagging by some angle, that is nothing but the minus pi. So this is the minus pi, this is the plus point, and this is the t is equal to 0. Now coming to this. Now if the voltage is like this, now in this fourth waveform, now voltage waveform is an alternating quantity shown with red color, and current waveform is also a alternating quantity shown with the black. Now these two waveforms starting, crossing at the 0 point, and again reaching to the 0 point is at the same instant. So there is no change of changing its value from positive to negative. It means that is a 0x. So starting at the same point, of course, reaching its peak is also at the same instant with the different magnitudes. And again it is these two waveforms, again voltage and currents are reaching to 0 at the same instant and going to the negative peak at the same value and again coming back to the 0 at the same instant. Only the magnitudes, that positive peaks are the waveform is having different value but having the same frequency, and starting, reaching to the peak and reaching to the 0, reaching to the negative peak, reaching to the again 0, is all these are happening at the same instant. So this is called as this voltage and currents are said to be in phase. So these two quantities are in phase. So naturally when it happens in the alternating circuits, now what is the reason behind this? Now with what parameters in the circuit this voltage and currents said to be in phase quantities means if the circuit is purely resistive, then this voltage and currents are said to be in phase quantities. So the angle between them is nothing but the 0 degrees. So generally we can define the power factor, that is the cosine angle between the voltage waveform and the current waveform. So this cos 0 is nothing but the 1. So this resistive is nothing but the, this is the example for unity power factor element. So this is about this one. And here in this particular waveform, the voltage which is shown with the red color and this current is nothing but it was shown in with black color, and this current is originating at some different points. Voltage is originating at the different instance. Voltage is originating at t is equal to 0 and the current is not at 0. It is something lagging behind. So how much of angle? That is nothing but the pi. So the voltage is reaching to its peak value at some other value and the current is reaching to its peak value at some other value. Now nothing is coinciding. Either starting points are reaching to the peak, are reaching to the again 0, again reaching to the negative peak, or coming back to the 0. None of the parameters are happening at the same instant. Now every instant if you could compare, there is an angle of difference is there. Now in the ideal cases, the angle is nothing but this is to be 90 degrees. But in the practical cases, what happens? This is less than 90 degrees. Now when this happens in the electrical circuits means if the circuit is nothing but the purely inductive or practically some practical inductance is there, then in such cases there will be a angle of difference between the voltage and current. So this is nothing but the phase difference, maximum phase difference between the voltage and current. If the circuit is inductive in the nature, that is 90 degrees. But in the practical cases, whatever the phase difference between the voltage and current, if the circuit is inductive in the nature, means less than 90 degrees. Now here this current is nothing but it is lagging the voltage V. So this electrical circuit is said to be lagging power factor. And third one is one more thing. So this red one, that is a voltage waveform, is originating at 0 and this current is nothing but it is some another instant. So that is nothing but the advanced angle of advancement is there. So by some pi, the same thing. So this is originating here. Either it may be originating here, and the voltage is nothing but it is coming like this. So again between here, voltage and current is also now reaching to the peak, originating at the starting at the 0 point, or reaching to the peak, again going back to the 0 point, again negative peak. None of the instants are happening at the same time. So this is here the voltage was lagged by whom? Current. Now here this current is nothing but current is leading the voltage. Current is leading the voltage because this current waveform is nothing but it was originated by some angle pi, which is nothing but it is an advanced angle. So this waveform, which waveform is advanced by how many angles? How many degrees means pi? Which waveform? Current waveform. So this is nothing but current leads voltage by 90 degrees in ideal condition, otherwise less than 90 degrees. So it is practical case. Now when it happens, this type of situation we can see in the electrical circuits if the electrical circuit is purely capacitive in the nature. So the power factor is nothing but the leading power factor. Now this analysis we can summarize with the simple waveforms. Now this green one, in this one, green is nothing but it is can be called as a voltage, or the voltage we can represent with this waveform, and lagging current is there. This is the lagging and this is nothing but the leading current. So you can say, so suppose this is nothing but the reference point. This is very, very important. This is the reference point. Now this point is nothing but angle of advancement, and this is angle of advancement means plus pi, and this is nothing but the lagging angle. So with respect to this reference point, this quantity, whatever it may be the quantity shown here, it was started some angle of advancement by, that is nothing but the plus pi. So this quantity is nothing but it is said to be a leading quantity. Either it may be a voltage or current, whatever it may be, this quantity is leading this particular quantity shown with the green color. That is about this point. So next one is one more quantity. Now this is the another quantity. Now that if you could compare this green one and this one, the green one is a reference one, and this one is nothing but it is lagging by some angle. So that is this particular quantity, this quantity here, this is nothing but the lagging quantity with respect to green quantity. So one more generalized notation, J notation, that is also called as it is a J operator, or in mathematics this can also be called as in the trigonometry, this is called as a I operator or J operator. The J operator is a vector quantity which when operates on a given quantity. Suppose if you are applying this J operator on any existing quantity, if I say take this is the O A quantity, on this one if you are applying the J quantity or I operator, then automatically this will be rotated by 90 degrees in anti-clockwise direction. Then the resultant is nothing but this is the J times of OA. So now initially the vector is this, OA is nothing but this is the vector. Now on this one what I am doing is I am operating or I am applying J operator on this. Then immediately whenever you are multiplying this existing vector with some J operator, then automatically the initial vector it will be rotated by 90 degrees, exactly 90 degrees in anti-clockwise direction. So now the resultant vector is nothing but this is OA only, but J times of OA. Now again here also if you are applying one more J operator, it will be rotated by furtherly 90 degrees here. So this is the one more 90 degrees in anti-clockwise direction only. So this is J times of OA. So this is J square of OA. So exactly if you are seeing this quantity and this particular quantity, now this quantity and this quantity are exactly in the opposite phase opposition. So this phase opposition means the magnitude is same. Now whenever you are applying a J operator on any quantity, now the magnitude will remain same, only it will be rotated by 90 degrees in anti-clockwise direction. So magnitude is same. So this magnitude and this magnitude is same, and only the angular difference it will be changed. So what happens? So J square is must be minus, because this quantity and this quantity are in the phase opposition. So what could be the value of J square? So this J square it will be minus, and anyhow the magnitude OA is nothing but this is the magnitude will remain same, only this minus will comes into picture. So j square can be approximated as minus 1. The same thing here. Now 180 degrees rotation is nothing but the minus 1. Again furtherly, if you are applying one more j operator on this vector, so it will come back to vertically downward direction. So again it is one more j operator. So this is j cube times of OA. So j square is minus 1. So minus j times of OA. So this is minus j. 270 degrees rotation. Again one more j operator if you are applying. So it will go back to the 360 degrees. So it will be plus 1. Means it will come back to the initial position. So based on our requirement, now in the complex analysis, because alternating quantities or alternating circuits are exactly, it will be in complex in nature. So if you want to define the complex parameter more exactly, this j operator is highly required for us. Now j operator, if it is rotated, now what is the impact of this j operator on the alternating quantities means? Now with this simple slide, we can analyze what this j operator, and if j operator is applied on any quantity, what will be the consequences. So these alternating quantities, these complex parameters can be represented in two forms. One is the rectangular form, next one is the polar form. Of course, this we know from the fundamental scratch level. So again, even though for our better understanding, again I am presenting this slide for your better understanding only, nothing more than this. Now sinusoids, so that is nothing but the alternating quantities, are easily expressed in terms of phasors, which are more convenient to work with the sine and cosine functions. So sine and cosine more or similar same, only the phase angular difference might be there between the sine and cosine functions. Now any rectangular or Cartesian or complex form means, suppose now if this is our x plane and this is y, so any point in the space is nothing but it can be represented as x plus jy. So that is, now here if you are writing like this, then again if any parameter is represented here, this minus x plus jy. So any quantity here minus x minus jy, any quantity here x minus jy. So more or similarly, you can represent any wave, any point in the space is in the rectangular coordinates a minus or plus or minus x plus or minus jy. So this is plus or minus x plus or minus jy. Now if any quantity is represented like this, now this form is nothing but it is called as a rectangular one. Now again, if you want to convert, suppose in some of the cases we may not have that much of flexibility in doing some examples with these rectangular components. Now you can convert these rectangular components into some polar form, that is z is equal to r at an angle of plus or minus theta. So our trigonometrical form, z is equal to r into cos theta plus or minus j sin theta. Exponential form, of course here this form and this form and this form, these three are very very important, and exponential is equal to z is equal to r into e power plus or minus j theta. Now anyhow, we have discussed about this representation of rectangular and polar forms. Rectangular coordinates can be converted into the polar coordinates. Now whenever you are seeing x comma y, these are nothing but the rectangular representations, and r comma theta are nothing but the polar coordinates. Now any points, suppose here if you are representing x comma y, then now let it be 0, and any quantity, suppose if you are joining this particular point to the center, to the origin, now it is making, or the length of this vector is nothing but r, and this vector is making an angle with respect to this x-axis, that is theta. So this is nothing but the theta, and this point, now what are the ordinates of this particular point? If you are extending, if you are drawing a line onto the reference point, now this is small x, and this is nothing but vertically this point is nothing but the y. So in this one, this x comma y, this is the way of representing rectangular components or rectangular coordinates. And this same thing, now instead of marking x comma y, what I am doing is I am joining this point to the reference point, that is center point, and this line or this particular side is making an angle of theta. So this What about the r? R is nothing but if r is represented as square root of x square plus y square. Now how we got this? R is equal to square root of x square plus y square means now. So suppose if you are assuming this side, now this is now exactly this is y and this is x, this is r and this is theta. Now in this case what happens? This r is known to me and this y-axis, this height is also known to me and this adjacent point is also known to me. Now if you are applying sine theta, so opposite side divided by this one. So this is nothing but it is a right angle triangle. It is making 90 degrees here. So what do you mean by that? So r square is equal to x square plus y square. So what about the r value? Square root of this particular value. So what about the side of this? So side is nothing but the x square plus y square. Now if you are cross multiplying this, again you will get whatever the y value and whatever the x, all these things. And what about the x here? R into cos theta. Y is nothing but the r into sin theta. What about the theta value here? So if you are applying tan theta for this particular triangle, so opposite side to the adjacent. What about the theta here? Theta is nothing but tan inverse of y by x. So if any quantity having a magnitude of r, and now if it is making an angle of theta, which theta is equal to tan inverse of y by x, then you can replace this rectangular coordinates x comma y with polar coordinates r and theta. So whatever the r value and whatever the theta value means, this is r and this is theta. Now you can convert this polar to rectangular also now by writing x is equal to r into cos theta or y is equal to r into sin theta. As we discussed in the beginning of today's lecture, that the alternating quantities will find additional opposition if you are comparing these alternating quantities with DC quantities. In the DC quantities, as we discussed that the DC quantities will only get opposition because of resistance of the line. But in addition to this resistance, some opposition, the inductance of the line will make for alternating quantities. That is called as a reactance. The reactance is nothing but in electrical and electronic systems, reactance is the opposition of a circuit element to a change in the current or voltage due to that element's inductance or capacitance. Now, in addition to the resistance, the inductance and capacitance will also offer some amount of opposition to the input quantities like voltage or current. Now, that is the main difference in terms of oppositions by the systems to the alternating quantities and direct quantities. In the direct quantities, only resistance comes into picture. In the alternating quantities, along with the resistance, some reactance will also comes into picture. That reactance, it will be offered by the inductor and capacitor of the circuits, or inductance and or capacitance of the circuit. So reactance is again measured in ohms only because it is also a one kind of opposition, and the symbol used to represent the reactance is nothing but the X. Suppose if it is offered by the inductor, that is XL. If it is offered by the capacitance, that is nothing but the XC ohms. Now, whatever the total opposition, the alternating quantities we see for the voltage and currents when it is applying or flowing into the circuit, means that is a total opposition offered by the circuits or offered by the elements to the incoming voltage or current is nothing but it is known as the impedance. So the impedance is defined as the ratio of sinusoidal voltage to the sinusoidal current. So whatever the total voltage and the total voltage, how much of current it will make into the circuit, that is nothing but the current. So the ratio between the voltage and current is nothing but from the basic Ohm's law, it is known as the impedance, that is the total impedance. So only the difference here is in the DC circuit, impedance is nothing but the resistance because there is no reactance in the DC circuits. But in the alternating quantities or in the AC circuits, the impedance and the resistance are both are different because in the AC circuit, reactance will comes into picture. So how we are going to calculate that impedance means impedance Z is equal R plus J times of XL, or Z is equal square root of R square plus XL square at an angle of tan inverse of XL by R. Because this is the same formula, this is just like of R at an angle of theta. So R is nothing but because this is just X plus JY term, Now what about the R value? R is nothing but R is equal to square root of x square plus y square. X is nothing but the R square plus y is nothing but the XL square. The same thing. Don't confuse with this. And what about the theta? Theta is nothing but the tan inverse of opposition. So this is the value, and this is offered by the inductance if it is assumed XL by R. So tan inverse of XL by R. Suppose if it is a series resistance and the capacitance. So for the capacitance, so minus and R minus JXC. So this is square root of R square plus XC square, and phase angle is tan inverse of XC by R. And if all these three, resistance, inductance and capacitance, comes into picture, Z is equal to R plus J times of XL minus XC, or that impedance is square root of R square plus X. So this total collectively you can represent as X value. So totally tan inverse of X by R. So here the additional point we have to remember that now in addition to the resistance, some reactance comes into picture. So resistance along with the resistance along with the reactance, now it is called as the impedance of the circuit. And in addition to impedances, resistances, other parameters we can define, that is admittance reciprocal to the impedance, and conductance reciprocal to the resistance, susceptance reciprocal to the reactance. Now this is the very simple cases. If you know the impedance of the line, if anybody wants to know what is the admittance, just to take the reciprocal, and similarly conductance reciprocal to the resistance, and susceptance reciprocal to the X, that is the reactance of that. One more important thing here is complex power analysis. The power is the rate at which is done. So what the power is? Now rate at which the work is done, that is nothing but it is called as a power. The power is the rate of energy transfer from one terminal or one point to the another point. At what rate that power has been done or energy flow happened, that is nothing but the power. Now in circuit excited by DC sources, the voltage and currents are constant. So the power is also a constant, because in this DC circuits, voltage and currents remain constant. It will not change with time, because this is a not alternating quantity, whereas in alternating quantities the voltage and current magnitude, it will be changed. So that's why the voltage and currents are constant, so the power is also a constant. This is called as an average power, or this is power is represented as V into I. If AC power, if AC source is there, the voltage and currents are sinusoidal quantities which varies with respect to the time. When voltage and currents are time varying quantities, the power is also a time varying quantity. This is called as an instantaneous power. Now this is, now see here, if it is a constant values, now represented with the caps letters V and I, but whereas if it is an instantaneous value, if it is varies with respect to the time, now generally represented with the lowercase letters. So small v and I. P is equal to V into I. The average value of sinusoidal function of full cycle is 0. We can take the RMS value of the voltage and current. The RMS value of voltage and current are complex, and so the power is also a complex value. As we know that the complex power is given by S, which is equal to VI at an angle of pi. So this angle is nothing but, now we can split this value as VI into cos pi plus J into VI into sin pi. So VI cos pi is nothing but, this is the capital P, VI sin pi is nothing but the capital Q. This capital P is nothing but, this is the active power, capital Q is nothing but it is a reactive power. So active power is represented with the kilowatt. That kilowatts are nothing but the units of active power. This is also called as a wattful power, and this is the actually required power. And Q is nothing but it is a reactive power, wattless power. This is nothing but the kilowatts, kVAR. This is the representation for the reactive powers. And how can we represent? Now just now we have discussed that kilowatt is nothing but the wattful power. Now it can be represented as the adjacent one to any triangle, and this is the kilowatts. This is nothing but the reactive power. Now this can be represented by this sign, because this kilowatt and kilowatts, this will make an angle of 90 degrees. The resultant one is nothing but the apparent power. This is S is equal to V into I. So these are the three different types of powers. you can see in the AC circuits. But in the DC circuits, only one constant power, voltage and current. If you are taking the product between them, you can see the total power the DC circuit will have. But whereas in the AC circuit, the powers are, again, there are three types of powers you can see. One is the apparent power. Now that is S is equal to V into I. And next one is this apparent power can be divided into two powers. One is the reactive power, one is the active power. And active power is nothing but the VI cos pi, and reactive power is nothing but the VI sin pi. So last one is the power factor. That is, what is the power factor? The power factor is the ratio of active power to the apparent power. Active power is VI cos pi and apparent power is VI. So if VI gets cancelled, you can see power factor as the cos pi. Now again, the same triangle, now we have represented with in different fashion. So this is VI, this is the VARs, and this is nothing but the watts. So the simple thumb rule here you have to remember is power factor is nothing but the cos pi. Now this is the angle difference between voltage and current. Now this is one of the important parameter in the electrical circuits. Now the power factor is. So this power factor may have unity power factor or lagging power factor and leading power factor. In today's video only, we have discussed when this unity power factor happens and when this lagging and leading power factors happens in the electrical circuit. We have discussed about this, and this is today's video session. Thank you one and all for watching this video. I hope this video has given good emphasis on the basics of different powers and complex electrical circuits, like whatever the real power, reactive power, and complex power, and impedance, reactances, and all these things. And finally, we have discussed about the power factor also. Thank you one and all. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.